In this lesson, we are going to be working with graphing functions, and very specifically, we're going to actually be graphing linear functions and some functions that aren't linear. Now, I just want to point out, there is an easy way of graphing functions that we're going to be dealing with in this lesson. And from the way that we're going to use, we'll be able to tell right away if a function is linear or not. And we're going to start off A and B using our method, okay? When we start off A and B, the method is called using a table of values. So what we're going to do is we're going to select one of these tables here. We're going to go into table A, and I'm going to select a bunch of X and Y values to plug into this function or equation. Now, before we get started, I just want to note that there is such a thing as a linear equation and a linear function. We've been dealing with these all year so far. A linear equation is an equation whose graph is a line. It's a very circular definition, but it's a definition. A linear function is a function whose graph is a line. Okay, and I just want to point out these are not right now in function notation. We'll talk about function notation later, but these are functions because for every x value, there's a single y value that I get out. If there's a y value for every x value, I wonder if I just chose a bunch of x values, if I could figure out what their corresponding y values are. And that's how we're actually going to graph these. So what I'm going to do is I'm just going to choose some x values, -2, -1, 0, 1, 2. Okay? Anytime you're asked to make a table of values, you should make at least 5 values in your table. And then if you still can't tell what the graph is, what shape the graph is, what you should do is add more values to your table until you can figure out the shape. Hey, now that I have these x values that I chose, and I just chose some, -2, -1, 0, 1, 2. I always like to choose a couple of negative values, a couple of positive values, and 0 so I could see where the graph crosses the y-axis. Now, what I'm going to do is plug in each of these x values to this equation in letter A to get a corresponding y value. So let's plug in -2. 2 times -2 is -4 plus 5. -4 plus 5 is 1. So I know that -2, 1 is one of the coordinate pairs. -1. 2 times -1 is -2 plus 5 is 3. I plug in 0. 2 times 0 is 0 plus 5 is 5. 1 times 2 is 2 plus 5 is 7. You're probably picking up on the pattern by now. 2 times 2 is 4 plus 5 is 9. All right, now, I could graph this. It's a little tough for me to graph on the computer, but I've done it before and I could do it again. However, what I'm going to do, since there's a little picture of a graphing calculator next to this, I'm going to use a computerized graphing method. Okay, I'm not going to use a graphing calculator. Instead, I am going to just take this table and we're going to go to Google Sheets, which is a program that allows me to put data into a spreadsheet. What I'm going to do is I'm just going to switch the orientation of this. I'm going to put my x and y's in columns. You'll see that the coordinate pairs here match the coordinate pairs here. It's just these are side by side. Okay, now I'm going to show you how easy it is to make a graph of something in Google Sheets. Once I have all of my x, y values plotted, here's my x coordinate, my y coordinate, my x coordinate, my y coordinate. I wonder how I can plot those. Well, if I go to Insert, and I choose to insert a chart. And I just wonder, yeah, there it is. This is the graph of my equation. Now notice, because all of my points were positive, this only shows above the x-axis, but this is the graph. And if I were to connect all of these points with a line, then I would have the actual graph of the function. Now, in letter B, I'm going to do the same sort of thing. I'm going to make an x, y table. But one of the differences here is I want to see a little bit more of this one. So I'm going to go -4, -2, 0, 2, 4. You can choose whatever x point you want. It doesn't really matter if you choose starting at -2 or starting at -4, counting up by 1s or counting up by 2s. You're always going to find corresponding y values, and you can always graph them as coordinate pairs. So if I plug in -4 to this equation here, it's going to be -4 squared is 16 plus 1 is 17. -2 squared is 4 plus 1 is 5. 0 squared is 0 plus 1 is 1. 2 squared is 4 plus 1 is 5. 4 squared is 16 plus 1 is 17. All right, let's see if we can graph this relationship. So it's going to be -4, -2, 0, 2, 4. And then my y values are 17, 5, 1, 5, 17. I got those by plugging in my x values into my equation. Now let's graph this. Insert, chart. There we are. Now, this one's probably going to look better as the scatter chart. And you can imagine that I connect all of these together with this smooth curve, this curved downward shape. We call that shape a parabola. This one makes a parabolic graph. Is it still a function? Yes, because it passes the vertical line test. Anywhere on this graph, if I draw a vertical line, if you can imagine that all of these are connected by a curve, anywhere I draw a vertical line, it'll only pass through one point. So this is a function, it's just not a linear function. We call it a quadratic or a parabolic function. All right, let's go back to our assignment. Now that I've done A and B and I've graphed them, notice the last question, decide whether the graph represents a function, yes, and whether it's linear. Well, the first one was linear, made a straight line. The second one was nonlinear, but it was still a function. All right, let's look at letter C. Letter C asks us to match an equation to one of two graphs. And what I'm going to do is I'm just going to imagine a table of values. If I wanted to, I could make a table of values for this one, but I don't really have to. So I'm going to imagine I'm plugging in 0 to get a y value. If I plug in 0, I get 0 out for y. Both of these graphs pass through 0, 0. So that did not help me at all. What if I plug in 1, though? 1 squared is 1 times -2 is -2. So it should go through 1, -2. Let's look like graph 2 is correct. Let's see what happens when I plug in 2. Notice that my x-axis counts up by 2. So where I have my cursor right now, that's where the 2 is. If I plug in 2, it's 2 times 2. 2 squared is 4 times -2 is -8. Does this pass through 2, -8? 2, 4, 6, 8. Yes. So letter C is graph 2. And the way I figured out that it was graph 2, I just plugged in some points. I found some XY coordinate pairs and I checked whether the XY pairs were on graph 1 or graph 2. Essentially, I created a table of XY values, except I didn't have to create a whole table of 5 of them. I could just verify that 2 of them were on this graph, but not on this graph. And then I know this graph has to be correct. All right. The next one, use the coordinates in the tables to match each graph with a table, one of these two. So let's do that. Y equals 1/3 x plus 1. Hey, they already made a table out of this equation by plugging in x values into this equation and figuring out what y was. -6, 2, 4, 6, and then -1. This one looks like it's going to have -6, -1. Let's see if it has the next one. -3, that's right here, 0. That looks right. 0, 1, halfway up between the origin and the first marking, which is 2. So letter D corresponds to graph 2. What about letter E? Let's see if that corresponds to graph 1. -3, that's going to be, let's see, because this counts by negative, so -3, -8. That looks about right. -2, that's going to be on this tick mark here, -5. 2, 4, 5. 5 is going to be right here. Yeah, that looks about right. 0, 1. Both of them have 0, 1 though. But this one had the other points correct. So this one is going to correspond to graph 1. So what you do to check these is just check the coordinates on your XY table. Listen, you're used to seeing graph coordinates in parentheses as an XY set in parentheses. But now we're looking at these tables as if this is a parenthesis set of coordinates. This is a parenthesis set of coordinates. And each one of these XY pairs can be graphed as a point. All right, let's look at letter F and G. Identify the domain and range. Whew, this is going to be the hardest kind of problem. The domain is all possible x values that you can plug into your equation, okay? So what x values can I plug in for this equation? What values can x take on? Well, I noticed that this graph stops at the y-axis. What is the x value at the y-axis? Well, it's not -8, it's not -4, it's 0. So the domain for this one is 0 is less than or equal to, okay, so normally I'd write the less than or equal to symbol with a less than and a line below it. That's just a little hard for me to do on a computer, so I'm going to use just less than or equal to in a row like that. 0 is less than or equal to x, and then it goes to infinity, so I'm just going to say is less than or equal to, and then infinity, so that would be my domain. I can plug in any number between 0 and infinity. Less than or equal to x, 0 is less than or equal to x. 0 is one of the numbers I could plug into this function because it touches the x-axis, the y-axis. All right, what about the range? The range is the possible y values this can take on. Well, it appears, if I'm counting up by 2's, that this graph starts at -1. So I'm going to say -1 is less than or equal to y is less than or equal to, and this one, notice that it keeps going up and up and up and up. It kind of looks like it might level off here, but it actually doesn't. Notice that the graph is still diagonal even when it ends. So unless there's some clear indicator that it's going to perfectly level off, if it's still increasing at the end, we just have to assume it's going to keep going up and up and up and up forever. So this one could take on an infinite number of y values. Okay, now this is a little confusing. This is going to take some practice, but please bear with me on this. All you're doing is you're looking for what values the graph can take on. This one obviously can't take on any x values less than 0, no negative values. So because of that, I'm saying that 0 is the lowest possible x value. X is going to be somewhere between 0 and infinity. That's all that this notation says. And again, I would use the less than or equal. The range is the possible y values. Notice that this starts at -1, and then y has to be greater than -1. The hardest part of this is realizing that this is going to just keep increasing and increasing and increasing forever. So it could technically go up to infinity if you have a big enough x value. All right, so, and maybe there's an argument that can be made that this should be less than infinity, because how's it going to be equal to infinity? That's a good question. I'm not sure that it really matters, and I wouldn't dock anybody's grade for that part anyway. But all right, let's go on to letter G. The domain and range of this one. Can you figure this out? Well, okay, this one's a little confusing when it comes to domain. There's no value you can't plug in for x, because notice it's still pointing diagonal here. It's not leveling off. Still pointing diagonal here. So that means that it keeps going in the left and the right directions. That means that my domain, and this is true for a lot of functions, for every linear function this is true, negative infinity is less than x is less than positive infinity. Because I can enter any number from negative infinity to positive infinity. But what am I going to get out for a range? Well, I'm going to find that the lowest number I can possibly get is 1. 1 is less than or equal to y, which is less than infinity. Because my y value can take on any number up to infinity as this graph gets bigger and bigger in either direction. Okay, hopefully that's not too confusing. But you have to state a domain and range sometimes, and to do that, you're going to state what values your graph can possibly take on.